point, and we're going to hear some more about that tonight. So our presentation here is free, of course, because we're online, but even when we were in person and hope to again, they're still free. So if you're in the area, stop by and watch us live in whatever. So what we try to do with these presentations is connect you all, the folks, the general public, with this exciting planetary and space science research that we're in this era of, if you will, it just keeps getting better. So as I said a little bit ago, this theme for this speaker series has been the James Webb Space Telescope. All the recordings of the previous presentations are on the LPI YouTube channel under the CESS playlist. This presentation will be up after tonight as well. So before we dive into the presentation, we have a few poll questions, as we always do. We like to get your feedback. So if you're with us online tonight, and if you're able to respond to the polls, please do so. The information we get from these helps us as we plan our future presentations and our future series. So Grace, if you want to go ahead and bring those up and walk us through them.
Sure. So I've just launched the first two poll questions. If you're on the Zoom app, you will be able to see these and interact. If you are joining us from the web browser, you won't be able to, or if you're watching on YouTube, of course. So for those of us who can interact, we wanted to know if you have attended one of our speaker series before. And if not, we are so welcome to have you. And secondly, we'd like to understand your current knowledge of the topic that we're going to be covering tonight. So how familiar you are with the JWST and its scientific mission. So I'm going to close this poll in just a couple seconds. Three, two, one. And I'll just show you all. We've got a good mix of people who have joined us before and some new people. Welcome. And we have a lot of people who are familiar with the mission, but there's always so much more we can learn. So I've got one more poll just to get a little bit more information about who is joining us. This helps us to plan our future programs. So you can select multiple options here, but we'd like to know which of these best describes you. Are you a scientist, any kind of educator, a student, an amateur astronomer? Maybe you're just a science enthusiast. And then finally, there's three options down at the bottom for where you're joining us from geographically. Are you local to Houston? Are you in the US, or are you international? So I'll give you guys a couple more seconds. Okay, and I'm going to close the poll. Thank you all so much for participating. That helps a lot. We'll have a couple polls at the end, so please stick around to participate in those as well. But for now, I am done.
There. Thank you, Grace. And thank you, everyone, for completing those polls for us. We really do appreciate it. So I'll tell you a little bit or introduce you to our speaker this evening, and then let her take the wheel and get going. Dr. Stefanie Milam she's a planetary scientist at the NASA Goddard Space Flight Center in Greenbelt, Maryland. And there she is the James Webb Space Telescope Deputy Project Scientist for Planetary Science. If ever there was a need for an acronym, that's one. She is from Houston originally, but she did her bachelor's in chemistry at Kansas Wesleyan University. And then she did her PhD in chemistry at the University of Arizona, where she sat in the basement of the Stewart Observatory building on the U of A campus as a grad student. Then she did a postdoc position at NASA Ames Research Center. And then she started at Goddard in 2010 as a research scientist. I could go on and talk about all this really cool stuff she does, like running these observing programs, these global observing programs. But I would feel less smart. So I'll just close out by saying that in 2014, she became the Webb Deputy Project Scientist for Planetary Science. So she is all about helping coordinate the observations or eventual observations of the solar system once Webb really gets going. So right now, I'd like to turn it over to you, Dr. Stefanie Milam.
Thanks so much for having me, and thank you for the lovely introduction. Let's just dive right in. So hopefully you're seeing my presentation, if I can get a confirmation on that.
Looks great.
All right, great, thank you. Okay, so as was said, I'm Stefanie Milam. I'm the Deputy Project Scientist for Planetary Science on the James Webb Space Telescope. First and foremost, I like to start out with saying that a lot of people associate the James Webb Space Telescope as being a NASA mission, which is true, but it is also a European Space Agency mission, and it is also a Canadian Space Agency mission. This is a joint partnership between these three agencies. Contributions of science, instrumentation, engineering, and technical advice. So, but this is a telescope for the scientists of the world. There is no allocation of time to any of these agencies and no obligation. All the science that will be conducted with the James Webb Space Telescope is peer reviewed, so that time is allocated based on whoever has the best ideas. So let's start with how this telescope actually was conceived. The Hubble Space Telescope director had an idea to stare at a blank piece of sky for about 100 hours or 100 orbits of Hubble, which is a considerable number of time or amount of time. And what they did was they looked at this sort of fingernail size patch of sky pretty close to where the moon is. And they stared at it for long periods of time, considering how oversubscribed the Hubble Space Telescope already was. And what they found was tens of thousands of galaxies. So what you're seeing here is actually the Hubble Ultra Deep Field. And what we did was we put it into perspective. So you could see that all of these galaxies that we were able to image in this tiny little fingernail spot of the sky, you can see all of these galaxies. And as we are going through them, we're actually stepping back in time. And what you'll notice is at some point, all of these galaxies are no longer these beautiful structures, but also we come to an end. The Hubble Space Telescope only has capability to see as far as it possibly can due to its sensitivity, but more importantly, due to the wavelength that it actually operates in. So in order to see further back in time, we have to push, and this is sort of giving you that scale of how far back in time the Hubble Ultra Deep Field could see. So we're talking like the early teenage years of the universe beyond the Big Bang. So to see the sort of toddler years or infant years, we have to push even further back into time. And that's going to be what the main driving force of the James Webb Space Telescope is. And so this is the primary goal, why the telescope was actually designed and built to be what it is today. So in order to see further back in time, we actually have to go to longer wavelengths. So this is why the James Webb Space Telescope is actually an infrared telescope, because the universe is actually expanding. The light that travels through this expanding universe is actually stretched to longer and longer wavelengths. And so this is how we get the cosmological redshift that you may or may not have heard of. But basically it's the light that we're seeing from stars and galaxies from the early universe that are emitting at the same wavelengths that ours do. So in the optical, UV, and sometimes even higher energy radiation, it's just traveling so far, it's getting stretched and elongated, that light actually is, and it shifts into the infrared. And so we had to have an extremely sensitive Hubble sensitivity, Hubble quality telescope that operated at infrared wavelengths. So what I'm going to do is I'm going to highlight some of the science that is driving the observatory, why we have the instrumentation, the design that we have, and some of the more intriguing questions that we're hoping this observatory is going to be addressing. And then I'm going to go into some of the technical details of the telescope, why we built it the way we did, and then show you some of the highlights of what we've actually been able to accomplish so far in the very short period of time that we've actually been operating in space. And then give you some perspective of what's going to be happening in the next few months. So let's just get right down to it. As I just said, the primary science goal of the James Webb Space Telescope is actually to study the very first stars and galaxies. But by doing this, you actually want to look and study galaxies as they've evolved through time. So what you're seeing on the left here is a galaxy that's actually pretty close to where we are as far as cosmological redshift. So almost the same age as, our own galaxy. And then as you go step across to the right, you're going further back in time and seeing how these galaxies have actually aged. So the one on the right, you see that it's very red. It doesn't have a whole lot of structure. And then as they evolve in time, so moving left across these images, you'll see that that structure starts getting first clumpy. And then maybe you start seeing some spirals popping out of them and maybe some more structure, but definitely far more beautiful. Some of this might be due to actual resolution, so just looking at these objects, but a lot of it probably isn't. And so this is something that the James Webb Space Telescope, with its impeccable resolution and at these longer wavelengths, can actually study in a good amount of detail. So understanding how they've actually evolved and also what they actually look like when they first began. So this is the primary driver of why we have the James Webb Space Telescope. At infrared wavelengths, though, we also have access to seeing things that we can't see at optical wavelengths. So just like clouds in our own sky block starlight or any light, so you can imagine going out on a cloudy day, you don't necessarily see the sun, or a cloudy night where you won't see the lunar eclipse. Clouds are actually obscuring to our own eyes the same way the clouds across the universe are obscuring to the Hubble Space Telescope. So what you're seeing on this video is one of these giant clouds that the Hubble Space Telescope took images of. This is called the Pillars of Creation. It's one of my favorite images. And what you're seeing is that we go from optical wavelength, and Hubble actually had a near infrared camera on it. And so they acquired the same image with that infrared camera. And what you see is most of that dust actually disappears. And as we go to longer and longer wavelengths, more and more of that dust will actually disappear. And we can actually see how stars and planets are being born in these giant clouds, and also all the objects that reside behind them. So we'll be able to understand this sort of complex nature of star formation and planet formation at the very infantile stages of these objects. And so this is something that's going to be a whole new era of star formation, planet formation with the James Webb Space Telescope. Black holes. Black holes are a hot topic today. It's been a very exciting day for sure. And the James Webb Space Telescope will definitely be studying black holes. We're not going to be doing these beautiful images like the Event Horizon Telescope was able to show us today, but we are going to be able to study them with a number of our instruments and actually start pushing towards the question and long-standing problem of what actually came first, the galaxy or the black hole. So by studying the environments of black holes, so all of the, by using spectroscopy, we can study the temperature, the pressure, the entire environment that surrounds that black hole in extreme detail. And with the resolution and sensitivity of the James Webb Space Telescope, we can do this for multiple black holes across the universe. And so by understanding these environments from various objects, we'll have further understanding into what's actually going on with these objects, and hopefully get some more insight that we can actually couple with things like the Event Horizon Telescope. So in case you didn't see it, this is the image that was acquired in the press release today from the Event Horizon Telescope. So this is an extremely spread out radio telescope array. And so what they were able to do was actually image the center of our own galaxy, which is amazing. And this is the image that was acquired. And of course, the first question that popped up on social media was, well, what is the James Webb Space Telescope going to be able to do if this is so amazing? And Great news. We actually have programs already planned to study this exact object. So this is Andreas Gaspar, who actually tweeted some about his program that he has with a co-I, Chi-Kwan Chan, and they are going to be studying the SAG-A system with a lot of details in the mid-infrared, so one of the instruments that we have on the James Webb Space Telescope. So you should go and definitely see this thread if you haven't already done so. It's a lot of fun, and it's really exciting to see how the collaboration is already getting started, and all the fodder is already there for how we can use multiple facilities to complement each other and really get the good nitty-gritty details of all of these objects across our universe. One of the really hot topics in astrophysics right now, though, is planets around other stars. So studying exoplanets is something that the James Webb Space Telescope wasn't even originally designed to do. When this observatory was actually conceived, there were no planets known around other stars. So it wasn't a capability that we ever even anticipated that we would need to have at the time the James Webb Space Telescope was conceived. And of course, as things progressed, we started discovering more and more, well, the first exoplanet, then the second, and now more and more and more, and we're up to over 5,000 known planets around other stars today. So one of the techniques for studying these objects is something called coronagraphy. So because stars are so bright, it's really hard to see the features or the signatures of very faint planets that are reflecting that starlight in the near vicinity. So the way we do this is we actually take just a black disk. You can almost think of cutting out a black circle of a piece of paper and putting it in front of your eye. And then you just see all the light and all the things that are around that black circle. And it's kind of the same thing. We're taking the brightness off of the star so that we can see the fainter objects in the nearby vicinity. And so this is something that we have implemented with a number of our instruments that are on board with the James Webb Space Telescope in a way that we can directly image planets around their stars. But the more common way to study planets around other stars is through transit spectroscopy. So this is when one of the planets actually passes in front of their star and it blocks the starlight the same way the coronagraphy does, but maybe not in a complete manner. So we see dips in the brightness of the star. And that dip, the depth of the dip is actually dependent on how big that planet is. And then we can also see things like if they're puffy planets. So if they have atmospheres or if they're solid terrestrial planets, something like Mercury or even Mars. So whenever we see the puffiness of the planet, though, we can actually study the composition of that atmosphere. And that's something of extreme interest to many astronomers all over the world. Of course, this is all leading to finding Earth 2.0. So this is a model of what Earth would look like if we were studying it with this technique. You can see all the major components of the Earth's atmosphere. And what we are hoping to do is actually see another planet that possibly has a spectrum that looks comparable to what we have on Earth. But more importantly, one of the things that is absolutely interesting about Earth's atmosphere is without life, without biology, or the processes that are happening because of life, we wouldn't have an atmosphere that looked anything like this. So what we're hoping to find with the James Webb Space Telescope are these peculiarities, chemistry that couldn't occur in a stationary, stable environment. Something has to be causing it to be different. And so that could be any kind of process. Of course, you can think about the early bombardment era of early Earth. So all kinds of things crashing into the planet. We had a magma sort of surface, a lot of dust obscuring, all the water wasn't there. And then think about how Earth has actually evolved. What are the major influences and what are those processes that influence what happened to our Earth's atmosphere? Things like volcanoes or any other sort of process that could actually occur that causes something to look peculiar. as we study these planets around other stars, that's what we're obviously looking for, these peculiarities. And that's just going to lead us with a short list of objects of real interest that have something going on in their atmosphere that we'll do follow-up studies, maybe with something as sophisticated as the Event Horizon Telescope, though probably not, we don't need that kind of resolution, but maybe a future generation space telescope, maybe one of the next 30-meter telescopes that are being built on the ground. There's all kinds of things that are being built and designed to study these planets around other stars that are going to have capabilities that are very complementary to what the James Webb Space Telescope has. And so this is sort of where we're going in the next phase of studying planets around other stars, and the James Webb Space Telescope is, of course, leading the way. Let me emphasize how challenging doing transit spectroscopy actually is. So we actually can measure transits in real time from Earth. This is a transit of Venus, actually passing in front of our own sun. Everybody knows that Venus has a very thick, very rich atmosphere. And I challenge you to tell me that you can see an atmosphere or the puffiness of Venus in this image. So you can imagine how challenging it is to actually study some of these planets. More importantly, if they have a very diffuse atmosphere, something like Mars, how hard that possibly is. But astronomers and astrophysicists and people designing telescopes and instrumentation have done an amazing job and pulled this out in such a way that we are studying atmospheres around planets fairly routinely now. So it's a very exciting time for sure. But James Webb Space Telescope is a fully capable observatory, the same way the Hubble Space Telescope was. And that means we can observe just about everything in the sky, including objects that are much closer to home. So we are able to observe objects in our own solar system. That's why they hired me, was to make sure we could do this. But with the funny shape of our telescope, we can't actually point it towards the sun. We have an infrared telescope. It's very sensitive to thermal heat. So the sun, the earth, and the moon all are very hot compared to what we want to observe in the distant universe. So we can't point our telescope anywhere towards the inner solar system. But the good news is we can, with our funny shaped telescope, point pretty much from Mars on out. But this includes objects like near-Earth asteroids, comets that come into the inner solar system, and hopefully things like interstellar objects. The brightest infrared object in the sky, however, is something close to home, and that's actually Mars. It was a real challenge trying to figure out if we could actually observe Mars with the James Webb Space Telescope. And the good news is we have opportunities to actually do so. You can see on the left-hand side, this is what some of our resolution and instrument capabilities look like with respect to Mars when it's in an observable position with respect to Earth. So you can see we'll have really good resolution so that we could do full maps, such as the one that you see on the right. The map that you see here is actually a map of methane that was published with a ground-based infrared telescope, the Keck Observatory. To acquire this map, it took many, many months, actually years, to accumulate enough data to make a full disk map of methane on Mars, especially to get down to the sensitivity level that they needed fighting with the Earth's atmosphere. With the James Webb Space Telescope, we'll be able to make maps like this within less than an hour worth of time. So we'll be able to actually monitor real-time weather patterns that are happening across the atmosphere of Mars. Study also things that we can't see from the ground, such as the night side terminator of Mars. So seeing how the environment actually changes going from day to night. We know the extreme temperature gradients that we have on Mars when we go from a nighttime epoch to a day. And so understanding what actually happens to the atmosphere, the winds, and other atmospheric features that could possibly occurring during these sort of transition phases is something of extreme interest for the whole Mars community. The other thing to consider, and a question I also get quite often, is we have an extensive Mars program with NASA. We have tons of rovers, orbiters, probes, you name it, it's probably there on Mars, and eventually humans will be there. Why do we care if we can actually observe Mars with a space-based telescope? And the whole reason we want to do this with any remote telescope is so that you get some context. You can imagine an orbiter only gets the perspective the same way as flying in an airplane. You only sort of see that ground or area just beneath where you actually are. Or a rover, you're only getting to sample or probe the area that's directly where the rover is. So understanding global characteristics is something that's very challenging to do with these types of spacecraft. So having a global perspective, especially one with the sensitivity of the James Webb Space Telescope, where we can take snapshots of the entire planet at any given instant and be able to understand what's going on in a real time, is something that's very valuable. And so this was a significant science case to ensure that we had the capability to do. The other hot topic in planetary science right now is ocean worlds. So we have a variety of satellites around the giant planets that we believe have these subsurface oceans. So beneath these icy crust or mantle-like layers, there's supposedly some sort of liquid magma type component to these bodies. We also believe that they have some energetics beneath that liquid surface as well. And so that is probably what is driving these plumes of gas that we've actually been able to observe, not only with the Hubble Space Telescope, but also with things like the Cassini mission that was orbiting Saturn. What we can do with the James Webb Space Telescope is very unique compared to the capabilities of these previous missions. With the wavelength coverage that we have, we can actually study the composition of the plumes of gas, as well as the surface around the plumes themselves. So you can imagine when a volcano erupts, we get a whole new refreshed surface on Earth of where the magma has redeposited, or the lava has redeposited on the surface, and it actually looks very different than any of the other terrestrial surface in the vicinity. We could probably see something like this occurring because of some of these plumes. If it is the liquid from the subsurface that's actually being spewed out, hopefully it will form some sort of a residue across the surface. So with the James Webb Space Telescope, we have this impeccable resolution, and that's what you're seeing when we have this grid pop up across the surface. That grid is the actual pixel size of one of our science instruments called the near infrared spectrometer. And each one of those pixels, we actually get a full spectrum that you see pop up on the right. So we can do the composition across the surface and look for these new deposits, icy lava type deposits, and we can also characterize the plumes themselves if we happen to catch them in activity. So this is going to be a really exciting era for studying these ocean worlds and getting the real details about what the composition of the subsurface ocean, and see if it's something that potentially could be habitable as well. The real bread and butter, though, for the solar system is the outer solar system with the James Webb Space Telescope. With the sensitivity and wavelength coverage, we can characterize every known Kuiper belt object to date. That includes some of your favorite characters in the outer solar system, including objects like Pluto and its large moon, Charon. These objects are very hard to image or study in any detail from the ground. And obviously sending missions to the outer solar system is very challenging in and of itself. And even when we do, we only get a glimpse of them at any given time because they have to be flyby missions. We haven't been able to design or plan a mission to actually orbit any of these objects in the outer solar system, just due to the limited resources that you have, lack of solar power, and lack of energy to be able to insert into an orbit. So by studying them remotely with really sensitive telescopes is our primary source of understanding these objects in the outer solar system, how our solar system actually formed, and how other planetary systems could possibly be following in the tracks that ours did. So this is something the James Webb Space Telescope will do very, very well, because at infrared wavelengths, we're actually studying the bodies themselves as opposed to the reflected light of the sun. And that's something that they don't do very well because they are so far away and they tend to be pretty dark anyways. So this is going to be one of the real niche areas from the James Webb Space Telescope in the solar system. All right, so that's sort of the highlights of science. I'm going to move on to some of our engineering challenges of building an extremely large space-based telescope and show you some of the amazing pictures and innovations that have come through this telescope. And I hope you have questions because there's a lot of information I'm not covering in this presentation. So the first thing I like to do is always give some perspective of how big the James Webb Space Telescope is. And we like to relate that to the Hubble Space Telescope because that's something a lot of people are very familiar with. So this is giving you a sense of scale. The James Webb Space Telescope has a sun shield that's about the size of a tennis court. It stands about 3 stories tall, and the primary mirror is about 6.5 meters in diameter, or just over 21 feet. The Hubble Space Telescope's the size of a tractor trailer, and the primary mirror is about 2.4 meters. So here's some of the statistics here for you. The Hubble Space Telescope was launched in 1990. It's primarily made of aluminum. It is very heavy. The mirror is one solid piece of glass, which is also extremely heavy. And it was a serviceable mission. It's in low Earth orbit. And astronauts were able to go and upgrade instrumentation as well as service the facility itself. The James Webb Space Telescope was launched on Christmas of 2021. We have a projected lifetime of 10 years. Again, the mirror is 6.5 meters in diameter. And one of the key things that I like to emphasize is to build such a large telescope and to launch it and send it 1 million miles away from Earth, we had to make everything extremely lightweight. So if you look at the mass of the James Webb Space Telescope, it's half of that of the Hubble Space Telescope when it was launched. This is extremely significant, and understanding the challenges that went into building such a large observatory that we could launch it into space and send it 1 million miles away was quite an extreme and quite an engineering feat. The other thing to emphasize is this 10-year lifetime. We had such a beautiful launch that we've now done some estimates of what our fuel cost is actually looking like. And we're probably pushing closer to a 20-year mission lifetime, which is absolutely phenomenal considering we don't have a serviceable observatory. And the final thing I want to emphasize is the operating temperature of these telescopes. Because the James Webb Space Telescope is an infrared telescope, we're looking for tiny little thermal signatures across the universe, these first stars and galaxies, and the radiation that they're giving off. So having an extremely cold telescope is something that was very challenging to do in and of itself as well. But the way we did this was we built a giant sun umbrella, like a beach umbrella. And by doing so, we actually are able to cool the telescope by just sitting in the shade and give it an SPF of about 1 million. So the hot side of the telescope is about 185 degrees Fahrenheit, or the bottom of the sun shield anyways. And then the cold side, where the telescope and the instruments reside, is almost negative 400 degrees Fahrenheit. So just sitting in the shade alone cools us down absolutely to a temperature that's well below anything you can probably fathom here on Earth. And then I also have the scales of the observatory just so you can get a sense of how big the sun shield actually had to be so that we could cool all the optics and the instruments efficiently. So again, it's about the size of a regulation tennis court. So how do you get something that big into the fairing of a rocket to launch and send it 1 million miles away from Earth? Well, we basically had to do some origami. So we take this huge telescope with its extremely large sun shield, and we start folding it up. First, we fold the mirrors so that the solid surface of the mirrors are actually folded behind. The secondary mirror pops up and over, and then we retract the sun shield and fold it up as well so that we fit inside the fairing of an Ariane 5 rocket. This is also a great time to point out that we did launch with Ariane Space. Our rocket was contributed by the European Space Agency, so this was not on the total bill for US taxpayers. Excuse me. And this is what it actually looks like in its launch configuration. I had the opportunity to go and see the observatory before it was sent off to French Guiana in the fall of last year. So it was a real honor to get to go in there and see the telescope. I actually cried. It was a very emotional period of time for me. But if we have a launch configuration of a folded telescope, that means once we get into space, we have to unfold it. So we had a very precise series of events that we had to go through to unfold the James Webb Space Telescope after launch. The good news is we had a whole month journey to get 1 million miles away from Earth. So we had plenty of time to make sure the observatory was unfolded by the time we got to our final destination. It was very piecemeal. It was 30 days of terror. Unlike the Mars rover, where we had the 7 minutes of terror, we had a full 30 days on the James Webb Space Telescope project. The great news is everything was absolutely beautiful. We had very nominal deployments, and everything was successful and working far better than we ever expected it would. This just is a testament to the success of our integration and test procedures that we did on Earth before we launched to ensure that everything was going to work the way that we wanted it to work. We had numbers of rehearsals and tests that went for years, practicing this whole sequence over and over and over again to ensure that everything would go flawlessly, and it absolutely did. Excuse me. And here it is. These are some of the final images, in my opinion, some of the most terrifying images of the James Webb Space Telescope. We took our beautiful observatory and we stuck it on top of a giant rocket. And then we put it into its own wrapping paper so that we could launch it into space on this giant rocket. Talk about being terrified, seeing your baby that you'd worked for a decade on sitting on top of a rocket. These are fantastic images. These were some of the final images that were taken of the observatory on Earth. We launched on Christmas Day from French Guiana. I hope you all were able to watch, and if you weren't, they do have the videos plastered all over anything you can possibly imagine, from YouTube to pick your favorite news channel. The launch was so nominal, you couldn't see the error bars in our actual trajectory compared to the predicted trajectory. It was amazing. It was really the best Christmas present I possibly could have asked for. This is one of the final images that was actually taken of the observatory before it became a small reflective dot in other cameras. We are currently at, actually this is 137 days now, launch plus 137 days. We completed all of our deployments as of January 8th, and we inserted into L2 1 million miles away from Earth on January 24th. While I say that's the last resolved image that we have at JWST, a number of people followed it on its journey out to the second Lagrange point. And there's videos like this all over the internet as well. These are fantastic, where you can actually see the observatory traveling to L2. So what is L2? Well, it's one of the Earth-Sun Lagrange points. It is a saddle point that's stable in orbit, that orbits the sun with the Earth. So we're always on the anti-sunward side of Earth, and we're in an actually very large elliptical orbit around L2. It is a saddle point, it isn't an actual gravitational point, so we do still have to burn fuel to stay there, and we also have to burn fuel to unload momentum. We don't have the benefit of using Earth's gravity the way the Hubble Space Telescope does to unload momentum, so we actually have to unload it with thrusters. So we are a fuel limited mission, but as I told you earlier, the good news is it looks like we're going to have something like a 20-year mission lifetime. And so just so you get a perspective of what this looks like as we go around the sun with the Earth, we're in this orbit. It is a kind of funny orbit, but we do have access to the full sky at least twice a year. Once we got there, we started doing our optical alignment. And so we have 18 segments of our primary mirror, and we had to make sure all of them acted like one mirror. So what we did was we turned on our primary camera, the near-infrared camera, and we just pointed the telescope at one star, a very bright star, and tried to see how well the mirrors actually did on their initial deployment. And this is what we got. This is all 18 segments pointing in total disarray at the same exact star. So the first thing we had to do was figure out which of these stars was associated with which segment, and then put them into the right place and put them in an alignment and focus them in their segmented place. These are real data. This is data that was actually acquired with the observatory. So here you go. You have the same star now 18 times, and then we focused it to make the images look like a fine quality. Then we went through a process where we actually started stacking each of those mirrors to make all 18 segments now act and look like one. And this is what the final image looked like once we completed that. And we even were able to take a selfie. This is a selfie before that final alignment happened. So what you're seeing is one segment's all lit up, and that's because the starlight's being reflected off of that one segment at that time. And of course, we all love our James Webb Space Telescope selfies. We have finally aligned now all of our science instruments. So this shows you what the footprint of all of our instruments looks like. We have the near-infrared spectrometer from the European Space Agency. We have the near-infrared camera from the University of Arizona. We have the mid-infrared instrument and imager that was provided by the European Space Agency as well as JPL. And then we have the fine guiding sensor, which is a fine guide camera so that we can point distantly, which is a part of the instrumentation suite with the near-infrared slitless spectrograph. And those were provided by the Canadian Space Agency. So this is what our final image looked like of all of our instruments being properly aligned with the optics of the telescope. And just for some perspective of how good we're actually doing, this is showing you a previous image acquired with the Spitzer Space Telescope compared to the Webb mid-infrared instrument. And you can just see the resolution and image quality is jaw-dropping. I cried at this image as well. It's been a very emotional 6 months for me. So here we are. Here's the commissioning timeline, showing you where we are with respect to all of this. We are starting our instrument commissioning. It's the final phase of our total commissioning, and we'll release our first images sometime this summer. But we just started a new Where is Webb page. So we were tracking our deployments, and now we're tracking this final phase of instrument mode checkout. So you can follow along and see how well we're doing with our instruments as we commission them through this last month and a half. So with that, I'm happy to take questions, and I can't wait until the summer when the first images are actually released and science begins. Thank you for your time.
Okay, thank you. Thank you, Dr. Milam. That was great. Good stuff. And I love the fact that you call it an observatory, because it's not just a telescope, right? It's a telescope with all the instruments. I love that. I love that. That's great. So we have a number of questions here. So let's go ahead and get into this. into these, see how many we can get through in about 10 minutes or so. How can the mid-infrared range study the UV flux output of the black hole in the Milky Way, the center of the Milky Way?
So I will say I am not a black hole scientist by any means. So what we're doing is we're not studying the UV light. We're studying the infrared light because we have an infrared observatory and how that is being influenced by the black hole. So with the spectroscopic techniques that we have on board the spacecraft, we can actually see line profiles of given molecular tracers that are emitting in the infrared. And so from those lines, we can see things like the dynamics of the system, how fast things are moving, how hot they are, also whether or not there's a lot of dust that's being trapped in various regions. And with the resolution of the James Webb, we can sort of map that out across. While it's not going to be this beautiful resolution that we got with the Event Horizons press release that we saw today, we will see a lot of good dynamics from just the spectra alone. And so I think it's going to be a really interesting field to see how things are compared.
Thank you. So here's a question related to comparing images from JWST with Hubble. Heard many people say that the pictures from Webb won't look like Hubble's. I know the wavelengths are shifted, but can't you do like a James Webb palette that substitutes RGB?
Yeah, so most of the images that you see with Hubble are not as your eyes would see them. So they take images with different filters and then they stack them up and make them look like the colors of the rainbow. So we can do the same sort of games with the James Webb Space Telescope because we have such a broad wavelength coverage. We can actually trace things like different molecular gases or different dust tracers, for example, and we can stack them in the same way. The nice thing is we have a resolution that's actually comparable to what the Hubble Space Telescope has. So we can even combine things like the Hubble telescope images and stack those with the James Webb Space Telescope in a very comparable resolution to understand things that maybe we could or could not see with the Hubble telescope, or that may be enhanced at longer wavelengths. So it's definitely going to be the same sort of games that we play with other observatories. And I mean, just look at these images of, that we've released earlier this week of the mid-infrared instrument. You can see the beautiful dust structure across the universe that we didn't even have the capability of doing with previous space telescopes. So I don't think we have to worry about how beautiful the pictures are going to be.
Great. And speaking of Hubble, what will happen to Hubble once James Webb is fully operational?
That's a great question. Hubble is healthy. It is in a nice stable orbit, and all of its instruments are working wonderfully. And we still actually have extra gyros even. So the Hubble Space Telescope is in a very good state and very good condition. We don't need to correct its orbit anytime soon. I heard the orbit's still stable for another 30 years. So it's just a matter of, as long as the instruments last, the telescope can actually last. So Hubble is currently funded for the next few years and will be operating. They do want to have an overlap between the two observatories because there's a lot of complementary science, as was just said, that can be done with the two telescopes, and something that I know a lot of people are very interested in doing. So what the plan actually looks like going forward actually just depends on the budget. If we have operational costs that can cover and support the Hubble telescope, along with the James Webb Space Telescope, as well as supporting future missions. The Roman Space Telescope is currently being built and expected to be launched in the next few years. So there's a lot of things going on, and maintaining a 30 some odd year observatory versus launching the next best thing. There's a lot of prioritization that comes at a pay grade well above mine.
I think we can all answer questions like that. So speaking of this 30-year time frame, wow, you guys asked some great questions. They're just segueing into each other. This is fantastic. So you mentioned that you think you can probably get James Webb, get 20 years out of it based off your early engineering data. Is it possible to get 30, or you just got to wait and see?
It all depends on the efficiency of operations, how often we have to do orbit corrections, momentum unloads, the efficiency of the science programs, how well we can schedule things so that we're not doing these big slews and saturating our momentum. This is a pretty conservative estimate just based on fuel usage and what our expectation was versus actual usage. So it's we'll see how it plays out. 20 years for infrared instrumentation is quite challenging. And, we're in a pretty harsh environment, and, we have very delicate materials that our observatory is made of. So we'll see how things actually go, what the contamination looks like after a decade. Maybe a lot of dust gets on the surface. There's a lot of things to think about, and there aren't currently plans to actually service the James Webb Space Telescope. So having a 20-year mission, I think, is a very big success story in and of itself, considering how long it took for us to get to this point. We will save the last bit of fuel, though, for the end. We're not going to go out with a bang, but we are going to go out with a thrust. So we're going to push the telescope out of L2 and sort of direct it away from the Earth, Moon, and other planetary bodies, just to make sure that it's not interfering with anything there, so that we can send more spacecraft there.
Cool. That'll be cool. Was there anything on James Webb, the design, that had to come off, that had to leave off? And was there anything that you specifically would have liked to have seen that didn't make it?
When I was brought onto the project, the first question I was asked is, what would you do with the James Webb Space Telescope? And I said, I would have put a higher resolution spectrometer on there. And unfortunately, when I joined the project, everything was already finalized. Actually, the instruments were being delivered to Goddard to start being integrated when I started on the project. So I didn't really get my hands in on any of the nitty-gritties of the details or specs of any of the instrumentation. So that being said, I'm a planetary astronomer using an astrophysics telescope. We'll use whatever you let us use, and we'll make it work. One of the things that I know that would have been a nice to have, or actually we'll see how things go. This is a really floppy telescope. It's giant. We basically have a sun shield made of happy birthday balloons. It's a very thin material. And so to make it slew and track something like a near Earth asteroid is really quite challenging. And to the point that whenever they're moving their fastest, or when they're the closest to Earth, is when they're actually really extremely interesting. But we can't make the telescope move quite that fast. And so one of the things we're going to try to do at the end of commissioning is really test how fast we can track some of these objects. So for the solar system, that's really significant, because we want to see things like interstellar objects when they're at the best optimal viewing. And if we can't track them when they're moving at a really fast pace, then it's really hard to acquire any data. So I think that's my biggest want right now. And it's just going to be, let's see what we can do. We launched with a certain speed limit that we promised to the community, and we'll make sure that that works, but I want to push it a little bit harder so that we can go a bit faster. It's my lead foot, I guess, growing up in Texas.
Great. So this question is about, so there's been a couple of interstellar objects that have kind of made their way into our solar system, at least that we've found over the past few years. And so there's a question of wondering if JWST might be looking for that, or if something on the ground here detects it, will it then like slew over there and look at it?
Yeah, absolutely. So we're not a searching telescope. It's not a surveying telescope. We actually have a really small field of view. So we're good at looking at things very small, very far away, very precisely. And to find objects that are moving across the solar system, you need a pretty good field of view with a certain amount of sensitivity. And that's how interstellar objects have been identified. As you see something streaking across the sky, then you do some follow-up observations and you track it moving so that you can get an orbit. If things are discovered, the James Webb Space Telescope is obviously going to do its best to look at them. that was my job, and 2 of my programs are designed just for that particular case. One is in case we discover a new comet, and one is in case we discover an interstellar object. So all hands are on deck. We're ready for this. If and when it's discovered, we will be observing it with the James Webb Space Telescope.
Great. Excellent. Well, we're out of time for questions. I think that's actually a great one to end on. A nice solar system question from our planetary scientists on James Webb. I know there's a lot of questions in the Q&A and chat box, so I apologize for not being able to get to those this evening. But thank you for asking them. We do appreciate it. And a big thank you to Dr. Stefanie Milam for coming on and presenting for us this evening and giving a great presentation to wrap up our series. We'll be announcing sometime soon our next series. That'll start in the fall. We've got some ideas. We just need to finalize that stuff, but we'll get there. So, I'm just curious. So Grace is going to put up a couple of more final polls for us. So we would really appreciate if you complete those for us. And just a closing thought I have for our presenter. Yeah, I lost it. So never mind. I had a question I wanted to ask you and I totally forgot what it was. So that's okay though.
That's okay, Andy. Maybe it'll come back to you. We'll give you a second to think about it. So while Andy sees if that comes back, we've got 3 evaluation questions. We just want to know how this program has affected your interest and awareness around the telescope and its scientific mission. And if you're likely to come back, as Andy said, this is the last talk in our 2021-2022 series. So we'll have a 2022-2023 speaker series starting later in the year. So you can look out for announcements about what our topic is going to be. And if you missed any of the talks in this series, they're all on YouTube. They're all about the James Webb. You can go catch up on topics that you missed, like astrobiology, exoplanets, and a whole lot more. And then finally, if you are interested in receiving notifications from the LPI about science breakthroughs, events coming up, anything like that, just check one of these boxes and we can automatically sign you up for one of our newsletters. All right, so a couple more seconds with the poll. Thanks all for participating. And once you leave here tonight, you're going to be sent automatically to a survey. We really encourage any responses that you all have, any suggestions. We take those really seriously. So I'm going to close the poll now. Thank you everyone for being here. And once again, like a big round of applause for our awesome speaker. Thank you for wrapping up our series. It was great.
Thank you so much. It was a lot of fun.
And thank you everyone for joining us tonight. We'll see you next time. We still live.